Okay, so if you remember, we defined the linear independence and dependence of vectors, right?
Yeah.
Okay, so then okay. So next we define what is basis vectors. Okay, so if every vector in a vector space W can be expressed as a linear combination of a given set of vectors, then we'll say then the set will say to be span that vector space W. So this set is said to span the vector space W. Okay. So here there are some few terms. So linear combination you remember, right?
Yeah.
Linear combination of a set of vectors. So let me give you an example. So W is a vector space, right?
Yeah.
And suppose S we have some set of vectors. Suppose V1, V2, Vn, right?
Yeah.
So suppose I take any vector U that belongs to W. I can write U equals to some alpha 1 V1 plus alpha 2 V2, so on up to alpha n Vn, right? So here these alpha I are scalars. Then this thing is called linear combination, right? Right.
Yeah.
Right. So if or any vector in this vector space W can be expressed like this for some scalars alpha 1, alpha 2, alpha n, right? Then we'll say that this set S spans the vector space W. Okay. So then we'll say that span of S equals to W. Fine.
Okay.
So up to this is clear?
1 minute.
Yes.
Okay, sir.
Right. So the next definition is called what is a dimension of a vector space. Okay. Let me write that. So the dimension of the vector space W is the minimal number minimal number of linearly independent vectors vectors in this that spans W. Okay, so what it is saying, the thing is linearly independent. This definition you remember, right?
Yeah.
Right. So linearly independent is that the vectors are said to be linearly independent if. Okay, so I think there's a spelling mistake. Mm, Right. So the linearly independent is so a set of vectors is said to be linearly independent if that alpha 1, alpha 2 up to alpha n, that summation is 0 implies that only the scalar solution is 0. All of them are 0, right? Okay.
Okay.
Right. So what I'll say is, so this one thing here you can observe that this spanning set. So this S is the set that spans the vector space W, right?
Yeah.
So it can. So here there is no condition about linearly independent or dependent, right? So in this case, it can happen that S is linearly dependent. This can happen. So here both choices are there. So it can be linearly dependent, or it can be linearly independent also. So here there is no restriction. Okay.
Okay.
So the dimension is, so if I can find a set S that is linearly independent and spans the W, so that will be also minimal, the number of elements, and that number of vectors in that spanning set, I will say that is the dimension of the W. Okay.
Okay.
Right. So let me write down. So suppose we will use the notation dim, the dimension. Dimension of W equals to K. Right. So then S we can find. So this is V1, V2 up to Vk, such that S is linearly independent. Linearly independent set, and the span of S. This is actually equals to W. Fine.
Yeah.
Okay. So this S, the set S that spans W and the size is equal to the dimension on W, we'll refer to that as a basis. Okay. So it is a basis for the vector space W. Fine.
Yeah.
Right. So if we take the k unit vectors, so that is a basis for the k dimensional vector space R power k. So let me write down. So this notation R power k, you know, right? So that is the k dimensional vector space, right? Right. So this is this type of elements are there, right? So there are k tuples, right? So C1, C2 up to Ck. So this R power k, you know, right? So for example, this 1, 2, 3. So this belongs to R3, right? Okay.
Okay.
Right. So here we are considering R power k. So the set of k unit vectors in Rk. So which set we are considering? Let me write down. So here you have 1, 0, 0. All of them are 0. Then the second vector is 0, 1, 0, and so on up to 0, 0, and the last one is 1. So this is a set of k vectors, right? k vectors. So this is called the natural basis or standard basis. Of Rk. Fine.
Mm-hmm. No.
Fine, right?
Yeah.
So next we will know what is a subspace of a vector space. So a non-empty subset of vectors in a space is called a subspace if the subset satisfies the axioms of the vector space. Okay. So here we are defining subspace. So it is a subspace of a vector space. So for example, so a vector space is trivially its own subspace that is already there, and the dimension of a subspace is the number of linearly independent vectors required to span the subspace. So this is dimension. So up to this much is fine.
Yeah.
Okay.
Oh, yeah.
Right.
Okay, sir.
Mm, right. So next what we have is give me 1 minute. Okay. So you know dot product, right?
Yeah.
Right. Next we'll define what is called orthogonal vectors. So two vectors are said to be orthogonal if their dot product is 0. Right?
Yeah, 1 minute.
Yes.
Okay.
Right.
Yeah.
And two subspaces are said to be orthogonal. Two subspaces are said to be orthogonal if to each other if every vector in one is orthogonal to every other vector in the second one. So if every vector in one is orthogonal to every other vector in the other. So let me explain. So here the notation we'll use, suppose u and v are two vectors, then if u dot v equals to 0, then we'll say that they are orthogonal, right?
Yeah.
And the second thing is, suppose capital U and capital V, so these two are subspaces. So we'll say that U and V, so these are the subspaces. As subspaces, they are orthogonal if suppose small u belongs to capital U and small v belongs to capital V. So this implies u dot v equals to 0, and this is for any choice of u and v. So if this is true, then we'll say that as a subspace, these two u and v, capital U and capital V, are orthogonal.
Okay.
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 Okay. So now, so you can see that the zero vector. So zero vector is the vector all the components are zero, right? So zero vector always belongs to the subspaces or vector space, right? So if I consider two subspaces, so given say W gamma and WS of the vector space WG, so it is always interesting to ask that what is the intersection of these two things. So intersection with WS. So we know that the zero vector always lies in the intersection, right?
Yeah.
Because the null vector or the zero vector. Okay. And one more observation is that if I consider the set of vectors in the intersection, So it is always a subspace. In the larger vector space. Fine.
1 minute.
Okay.
Oh,
Right.
yeah.
So, but on the other hand, what about union? So, if I want to do union of two subspaces, so we cannot always say that that will be a subspace. So, let me write down. So, on the other hand, the smallest subspace containing both W gamma and WS must also contain the union. Right. But in general, the union may not be a subspace. Fine.
Yeah.
Okay. So next point is the subspace that is spanned by the union of two subspaces, that is W gamma union WS, is called the join of W gamma and WS. So here the new term is join. It is a join of two subspaces, and it is denoted by this notation. So this is the join of W gamma and WS.
Okay.
So there is a nice relation between the dimension. So how to find the dimension of W comma join WS in terms of the dimension of each of them and their intersection. So that is the next observation, that dimension of W comma join WS, that is nothing but dimension of W comma plus dimension of WS minus dimension of the intersection. So we know that intersection is always a subspace, right? So that's why it will work out. Right?
Okay, sir.
So the next point is, so two subspaces of a vector space are said to be orthogonal complement are said to be orthogonal complements if the subspaces are orthogonal to each other. So here the term is orthogonal complement. Are orthogonal to each other, and they together span the entire vector space. Okay. So for example, suppose your original vector space is W, and you have two subspaces W gamma and WS. So they are orthogonal complement. So W gamma intersection WS. So that will be only the zero vector that I know. And for every x belongs to W gamma and y belongs to WS. So we have x dot y 0. So that implies that they are orthogonal. And whenever you take the span of the union, they uh, complete the whole space W. Fine.
Every 1 minute.
Yes.
Okay, sir.
Okay. So if you remember, so yes, so we introduced one type of matrix, right? So that is the incidence matrix, right? The vertex edge incidence matrix that we did, right? Okay. So this you remember, right? And we saw the properties of the incidence matrix. Okay.
Okay, sir.
So we'll do a theorem based on that. So we'll find actually the rank of an incidence matrix. So let me state the theorem. So if A of G is an incidence matrix of a connected graph G with n vertices, the rank of this matrix is n minus 1. Okay. So is the statement clear?
Okay, sir.
Statement is clear, right?
Yeah.
Right. So let us see how to do it. Okay. So let us consider each row of an incidence matrix as a vector. So let the vector in the first row be A1, then the second row is A2, A2 and so on. So how does the incidence matrix look like? So now our AG, so on up to n. So there are n vertices, right? So there will be n rows.
Okay.
So now we know that each column has exactly two ones, right? That we know because each column is representing an edge, right?
Yeah.
So there will be only two ones, right? One each for endpoint of that particular edge, right?
Yeah.
Right. So since there are exactly two ones in each column, of a the sum of these vectors will be zero, right?
Yeah.
So yes, since we are taking in modulo 2, okay. So
Okay.
our field is GF modulo 2. Sum of these vectors is zero in modulo 2. Okay. So what you can say is, so since the sum is zero, so we can say that these are not linearly independent, right? So what I'm saying is, so a1 plus a2 plus an. So this is equals to the zero vector, right? Because we are considering in modulo 2, right?
Yeah.
So from here I can say that these vectors, so this implies this collection AI is not linearly independent, right? By definition. a1 a2 up to an, right?
Yeah.
So since they are not linearly independent, therefore the rank has to be less than n, right? Because there are n vectors. So rank is the number of linearly independent vectors, right?
Yeah.
So therefore the rank of A is strictly less than n, and so this implies rank of A is less than equals to n minus 1, right? So we have to prove that rank of A is n minus 1. So now we have to do the other way. So we have showed that it is less than equals to n minus 1, right? Fine.
Yeah.
So now what we consider is, so now we consider sum of any m of these n vectors. These n vectors. So with one condition that am has to be less than equals to n minus 1. And if the graph is connected, then AG cannot be partitioned into a block, right? So like this means I cannot partition AG as AG1 0 0 AG2, right? So this way we cannot partition, right? Such that AG1 has m rows and AG2 this has n minus m rows. So this is only possible if it is if the, so it is actually highlighted point is cannot be partitioned. So you cannot partition like this. So this was only possible if the graph was disconnected, right?
Yeah.
Right. So in other words, we cannot find. So no m cross m submatrix of this AG exists. So can be found such that so where m is less than n minus 1, that is already given, such that if I take modulo 2, the sum of the rows is not equals to 0. Is equal to 0, right?
Yes, sir.
Right. So now since we are considering modulo 2, the only two scalars that are available, that is 0 and 1, right? Because in modulo 2 that are the only two scalars available, right?
Yeah.
So no linear combination of m rows can be equal to 0, right? Where m is less than equals to m minus 1. So no linear combination of m rows where m is less than equals to n minus 1, that is already given, can be equals to 0. So, but so this implies that the rank has to be at least n minus one, right? Rank of A is at least n minus one. So now we'll combine these two results. So this is my first equation. So rank is less than equals to n minus one, and this is my second equation. Rank is greater than equals to n minus one. So combining 1 and 2. So we have that rank of A is exactly equals to n minus 1. Okay, see the proof once.
Okay, sir.
Fine.
Yeah.
Okay, so here if you remember, so in the statement we have mentioned that it is a connected graph, right? So actually we can extend the theorem if the graph is not connected, and if there are k components, so then the rank will be n minus k. Let me write down. So what is saying? So if G is a disconnected graph, with n vertices and k components, then the rank of the incidence matrix, so rank of AG is equals to n minus k. Okay.
Okay, sir.
Okay. So now we'll look into the special case when G is a tree. So if you remember, so suppose we take G is a tree now. So n is the number of vertices, right? What is the number of edges?
E.
Yes, e. But in terms of n, actually we can write down the number of edges, right?
N
So it is
minus
n minus one, right?
N minus 1.
Right. So there are n minus one edges. So the what will be the size of the incidence matrix? So it will be n into n minus one, right? Okay.
Okay, sir.
So I know that there is a the rank of the incidence matrix is n minus one. So if I delete one of the edge, right? So if I consider the reduced incidence matrix, okay,
Okay, sir.
right. So then it will be a n minus one cross n minus one matrix, right? Okay.
Okay, sir.
So then it will be then it is actually a non-singular. Then the matrix, the reduced incidence matrix, will be non-singular.
Will be?
So it will be non-singular. Non-singular means the
Okay.
rank is full rank, right? My determinant is not equal to 0.
Okay, sir.
Right. So that is the corollary. The reduced incidence matrix of a tree is non-single. So fine.
Okay.